Hello friends, today we'll discuss our next topic, that is quality of service. The quality of service is the most important topic in the computer network. Why? The reason is because in the quality of service we have to improve the quality of any of the service. Example, in the computer network we only have to send the data. So how we can improve the quality of service? How we can send the data very fast at a good speed and there is no delay, the proper synchronization. So that's why we have the topic of quality of service. Well, to improve the quality or just to check out the quality, we have various flow characteristics. Well, if we talk about the flow map, that means the sending of data. So to send the data or to control the flow, we are having the four flow characteristics. The first one is the reliability, second one is delay, third one is jitter, and the fourth one is bandwidth. So first of all, we will discuss about the reliability. Well, the reliability is most important issue in the flow characteristics because we have to see that how much reliable a connection is or how much reliable we can send the data. The lack of reliability means losing a packet or acknowledgement. Whenever any of the communication system lose the packet so many times, that means, example, a source is sending the packet to the destination and their loss of packet rate is very high, that means the reliability is very less. If the packet delivery rate is very high as well as the packet discarding rate is very low, that means the connection is reliable. So the next one is the delay. From source to destination, the delay is the most important topic because whenever we are sending the data from source to destination, how much time a packet will take, that is called the delay. If the delay is very high, that means the flow characteristics are not good, the connection is not good. But if the delay is very less, in that case the characteristics of flow are very high, the connection is very good. The application can tolerate delay in different degrees. For example, if I am talking about the high degree, or if I am talking about the minimum delay required in applications like video conferencing or the audio conferencing or the remote login. So if I am talking about the delay, for example, we are doing the video conferencing, this video is streaming at the both parties from the source and destination, both are in the conference. So in that case, if we are having a small delay, that means the video will blur out. So the delay is required in very less amount. So that's why delay must be very less. If we talk about the audio conferencing, that is the same case as the video conferencing. And obviously if I am having the remote login, that means I am taking the another system and my own system, and in the remote login, if I will just click on the mouse or any of the entry, in that case, if the action is not performed at the same time, in that case, the connection is not good. So delay required is very less. So that is again the very important issue in the flow characteristics of the quality of service. The next one we are having a jitter. So what is jitter? Jitter is basically the variation in delay for packets belonging to the same flow. Now to understand the jitter, let us take the example of the packets. For example, we are having 4 packets. For example, P1, P2, P3 and P4. Now we are having these 4 packets, and let us suppose we are sending these packets at starting time. For example, the starting time of P1 is 0, P2 is 1, P3 is 2 and P4 is 3. These packets received by the destination, the time will be, say let us suppose it's 20, 21, 22 and 23. This is the particular receiving time of the packets. We are stating as the ST as the sending time and the RT as the receiving time. For example, if I am going to count the delay will be 20 minus 0, that is equal to 20. Again 21 minus 1, that is 20. 22 minus 2, again 20. 23 minus 3, again 20. That means the delay is constant, that is 20. But let us suppose I am going to send the packet as a 0, 1, 2 and 3, the starting time, and let us suppose the receiving time is quite different. If we are having one more receiving time, that may be the 21 for P1 and 23 for P2, again 21 for P3 and 28 for P4. So these are the receiving time. So in that case, the delay will be quite different. So the delay is 21 minus 0, that is 21. 23 minus 1, that is 22. And 21 minus 2, that is 19. 28 minus 3, that is 25. So we can conclude one thing. If I'm talking about the first receiving time, we are having constant delay. The delay is constant, that means we can say that the jitter is very low, because the difference between the sending and the receiving of the packet is very small. Then we can say that low jitter. And obviously the low jitter is required for the audio and video, because if you have to send the particular audio and the video, in that case the delay must be very less. That means the jitter will be very less. The low jitter is required. But if I'm talking about the second delay, the delay is very high, or we can say that it is the variable delay. As we are having the variable delay, that is, the delay is very high, so we can say the high jitter. And the high jitter is not acceptable and not suitable for audio and video. That means for sending the audio and the video file, we need to set the low jitter, and for low jitter we need a good connection. And good connection, that means the constant delay is required. Now, the next one we are having the bandwidth and the flow characteristics of quality of service. The bandwidth is required for sending of the data. That is, example, we want to send the data from source to destination. The bandwidth is required. That bandwidth is all about the sending of data or the speed of data. Different application need different bandwidth. For example, if I'm talking about the high bandwidth that is required for video conferencing. Now, if I'm talking about normal email, the low bandwidth is required. So we can say that the low bandwidth is required for sending an email. Because in the email we are having the low data. We have to send only the text file or maybe the video or the small pictures. So in that case the bandwidth, that is the speed of the data connection, is very less. So the low bandwidth is required. If I'm talking about the video conferencing, we have to send the synchronized of data, video and the audio. In that case, what we need? The high data rate, high connection, that means high speed. That is all about the high bandwidth. So bandwidth is the most important flow characteristics of quality of service. So we have discussed about the 4 flow characteristics, that is the reliability, that means how much connection is reliable, then the delay, that means the sending and receiving of data, we are having some delay, then the jitter, the variation in the delay, and the bandwidth, the speed required. Now, we will discuss the techniques to improve the quality of service with the help of these flow characteristics. So now we have to improve the quality of service. Here Q stands for the quality of service. Then we are having the 4th step, that is scheduling. Next is traffic shaping. Next is resource reservation. And the last is admission control. And the improving quality of service, that means we have to improve the quality of service. We are having the 4th step, that is the scheduling. If I'm talking about the scheduling, the packets from different flows arrive at the switch or the router for processing. A good switching technique treats the different flow in a fair and appropriate manner. Several scheduling techniques are designed to improve the quality of service. The first scheduling technique we are having, that is the FIFO queuing. The next technique under the scheduling we are having, that is the priority queuing. And the next under the scheduling we are having, that is the weighted fair queuing. So first of all, in the scheduling we will discuss the FIFO queuing. Under the FIFO we are having the FIFO, that is called the first in, first out queuing. For example, we are having some particular packet that is received by the destination first or the router first, then it will serve that packet first in. To understand FIFO queuing or the first in first out queuing, let us take the example of a diagram. Let us suppose we are having queue. Let us suppose we are having some packet. The first of all packet will be arrived to the decision box. And the decision box will check whether the queue is full or not. Now, for example, in the queue we are having the 2 entries which are filled. That means the queue is empty. It is not completely filled. In that case, the packet will be sent to the queue. But if let us suppose the queue is full, in that case it will discard the packet. Now the packet will be sent to the queue and queue will take that particular packet at the back side exactly after the 2 packets. Now after the queue we are having a processor in the FIFO queuing. So the packet is sent to the processor, and the processor will process the packet and will then send for the departure. So that we can say that this is the first come, first serve, that is the FIFO, first in, first out, and that is the packet is arrived to the queue and is processed and sent out. Next we are having that is the priority queue. In priority queuing, packets are first assigned to a priority class. Each priority class has its own queue. The packets in the high priority queue are processed first. Packets in the low priority queue are processed last. So to understand the priority queue, let us take the example of the diagram. Suppose we are having two queues. We can say that the first queue, that is the high priority queue, and the second one is the low priority queue. Before the queue, we are having the same decision box as we have earlier discussed. We will check out whether the queue is full or not. First of all, the data packets will arise and they will be sent to the classifier. After the arrival of data packet, the classifier will take those data packets and divide the data packet accordingly. For example, the data packet is of high priority, it will send the packet to the high priority queue, and the packet is of low priority, it will send it to the low priority queue. Then, after the priority queue, we are having the processor. The processor is having a switch that will be connected to the both ends of high priority and low priority queue, but one at a time. At the both ends of the queue, we are having a particular button to which the queue will be connected and the switch will connect to that particular area. Switch will send the data to the particular processor. Now let us suppose we are having the any packet. The packet will be arrived to the classifier. The classifier detects that the packet is of high priority. It will check out whether the queue is full or not. If the queue is not full, it will send the packet to the high priority queue. And after the high priority, processor will come to know the packet is coming from the high priority. Then the processor will indicate to high priority and the switch will take the packet from the high priority queue. Now whenever the queue is full, the switch will be switched to another queue from the high priority to the low priority. Now the processor will take the data packet from the switch of the high priority and it will send the data packet outside for the departure. So that is all about the priority queuing, in which we have assigned the priority with the help of the classifier. Next we are having the weighted fair queuing. Now the better scheduling method is the weighted fair queuing. In this technique, the packets are still assigned to different classes and admitted to different queues. The queues, however, are weighted based on the priority of the queue, maybe the higher priority. Higher priority means higher weight. The system processes packets in each queue in a round robin fashion with the number of packets selected from each queue based on corresponding weight. To understand the weighted queue, let us take the example in which we are having three queues. These are the three queues. We are going to assign the weight to all the queues because this is the weighted fair queuing. The first queue we will assign the weight as the 3. The second queue the weight is 2. To the third queue the weight is 1. Now all these three queues have the decision box as the prefix. Before the decision boxes we are having classifier. After the queues we are having the processor as well as the switch. The switch is connected with the processor. All the three queues are connected with the switch. Now let us suppose there is a arrival of the first packet. It is sent to the classifier. Now when the packet is arrived to the classifier will send the packet to the particular queues. Now we are having the three queues, having the weight 3, weight 2 or weight 1. Now if the queue is full, it will start the packet, otherwise the packet is sent to the particular queue. Let us suppose the packet is sent to the weight 3. Now in the processor we are having the switch which is connected to all the queues. Now the switch is rotatory. Now, the switch is connected to all the queues and the processor. The switch is rotatory in the clockwise direction. The direction and the connectivity of switch is first assigned with the weight 3 queue. Now the switch direction can be rotated from weight 3, weight 2 to weight 1 in the clock or the anti-clockwise direction. Let us suppose the switch is first connected with the weight 3. That means it will take 3 packets from the Q1. Now it will pass to the processor and the packets will be departure out. If the direction of switch is set to the queue number 1, that is of weight 3, then it will take the 3 packets and process them. Next, it will check out the wait to queue and will take the 2 packets from the 2 queue. Then next will come to the queue 3, it will take a single packet because the weight assigned is 1. So that means if the weight is 3, it will take 3 packets. If the weight is 2, it will take 2 packets. If the weight is 1, it will take 1 packet. So that is all about the weighted fair queue, in which the packets are based upon their weight. They will depart the packet according to their weight. Now we will discuss the next quality of service improvement technique, that is traffic shaping. Traffic shaping is the mechanism to control the amount and the rate of the traffic sent to the network. Basically, we are having 2 types of traffic shaping techniques. The first one is the leaky bucket. The next technique we have is the token bucket. So first of all, we will discuss the leaky bucket. Well, the leaky bucket algorithm shapes bursty traffic into fixed size traffic by averaging the data rate. It may drop the packets if the bucket is full. To understand the leaky bucket, let us take the example of the diagram. Now let us suppose we are having a bucket. In the bucket at the bottom, we are having a hole. Now let us suppose we are having a tap that is over the bucket. Now this tap will spread the bursty data. Bursty data, that means there is no particular sequence or the variable. The data can be in particular form, that is not constant data. That's why we called it as the bursty data. So the tap will spread the bursty data on the bucket. So it is a bursty flow of water. Now that water will be collected inside the bucket. So this is the bursty data or the bursty water. So we call it as the bursty flow of data. As you can see that at the bottom there is a hole in the bucket. That means there will be water which will come out from the hole. There is a main and the major point to be noted. That from the hole the data will come out or the water will come out. That means that will be of constant flow. So we can say that with the help of the leaky bucket, the bursty flow of data or the water can be converted to the fixed flow of data or the water. Now compare it with the networking terms. So example, we can say the data and the bursty form. Let us draw a graph for that. Suppose we are having a timeline on the x-axis and the data rate on the y-axis. I am going to divide the timeline into 10 particular parts, starting with the 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now let us suppose for first 2 units of second we are having 12 MB of data. So data rate will become 12 Mbps. Now suppose for the next few seconds system is ideal, and after that from 7 to 10 we are having 2 MB of data. So 2 MB of data, that means it's of 2 Mbps. So we can see that for the first second we are having data of 12 MB, that is 12 Mbps. And for the next few seconds the data rate is ideal, and after the next 3 seconds we are having 2 Mbps of data. So we can also state that this is the bursty form of data. So we can also consider as the bursty data. Now compare it with the leaky bucket. In the leaky bucket we are also having the bursty data or the bursty flow. That means sometimes the flow is very high and sometimes flow is ideal, and again for some time the flow become very low. 12 Mbps, 0, 2 Mbps, same in the graph. Now as we follow the leaky bucket algorithm, the data must be of fixed flow. So that means if we count the complete data rate, the complete data rate is 12 into 1, that is 12, plus 2 into 3, that is equivalent to 12 plus 6, that is equivalent to 18. That is in total we are having 18 Mbps of data. Now whenever we find out the fixed flow after the leaky bucket, we will modify the diagram of the graph. Now let us suppose we are having the complete data, that is the fixed flow data, that is of 1.8 Mbps for the whole 10 seconds. Now the data rate is of 1.8 Mbps and data is 1.8 MB for the whole 10 seconds. So we can say that 1.8 into 10 is equal to 18 MB of data. So we can say that it is the fixed rate data. That means in the leaky bucket, the bursty data or the bursty flow can be converted into fixed data rate. So with the help of these graphs and the diagram, it is quite clear that the bursty data of 12, 0 and 2 Mbps can be converted into directly in 1.8 Mbps, and the data can be sent in the constant rate. If a bucket has a small hole at the bottom, the water leaks from the bucket at the constant rate. As long as there is water in the bucket, the rate at which the water leaks does not depend on the rate at which the water is input to the bucket unless the bucket is empty. The input rate can vary, but the output rate remains constant. Similarly, in networking, a technique called leaky bucket can smooth out pulsy traffic. So that's all about the leaky bucket. Next we are having the token bucket. The leaky bucket is very resistive. It does not credit an ideal host. For example, if a host is not sending for a while, its bucket becomes empty. Now, if the host has bursty data, the leaky bucket allows only an average rate. The time when the host was ideal is not taken into account. So, on the other hand, we are having the next algorithm, that is token bucket. The token bucket algorithm allows ideal hosts to accumulate credit for the future in form of tokens. For each tick of the clock, the system sends n tokens to the bucket. The system removes one token for every cell of data sent. To understand the token bucket, let us take the example. Suppose we are having a bucket as the previous one, the leaky bucket. Now we are having a bucket, and in the bucket, at the place of water, we are having the tokens that will be generated at the particular tick. That means at every tick, the tokens are generated. So example, the token is generated. We can say that the one token is added per tick. Tick is the time. Now the tokens are collected inside the bucket. Now the one token removed and discarded per cell transmitted. Now that discarded token can be added to the particular queue which we have discussed in the scheduling. Now we will add the scheduling queue. Now first the package will be arrived to the queue. We will check out the queue is full or not. If the queue is full, in that case we will discard the packet. Otherwise we will send the packet to the queue, and the packet will be added to the help of the token, and the one token per tick is removed, and that will be added after the queue. And after adding that token to the queue, we will send it to the processor, and the processor will process the packet and departure the packet. AD stands for the departure. So that is all about token bucket. The token bucket can easily be implemented with a counter. The token is initialized to 0. Each time a token is added, the counter is incremented by 1. Each time a unit of data is sent, the counter is decremented by 1. When the counter is 0, the host cannot send data. The token bucket allows bursted traffic at a regular maximum speed. So the next we have the resource reservation. Admission control refers to the mechanism used by a router or a switch to accept or reject a flow based on predefined parameters called flow specification. Before a router accepts a flow for processing, it checks the flow specifications to see if its capacity, just like the bandwidth, buffer size, CPU time, etc., and its previous commitments to other flow can handle the next flow. So it is the mechanism used by a router or switch. The router and switch, they both check the flow specification before the admission of data. So that means before processing any of the data, router or switch will first check the flow specification. That is all about the admission control. So today we have discussed the quality of service and how to improve the quality of service. So that is all about. Thank you.